Okay, today we're talking about properties of logarithms. The three properties of logarithms, we've got the product rule, which is that log of a times b is log of a plus log of b. This one right here. The quotient rule, log of a over b is log of a, and this time it's minus log of b, so this second property. And the third property of logarithms is that you can move any exponents down and it becomes multiplication. So log of a to the power c is actually c times log of a. The properties are actually listed for base 10 here. So for example, on the first property, you can just assume that there's a base 10 right here and everywhere else. Because whenever you write a log with no base, you assume it's base 10. But it turns out that these three properties of logs will hold for any base as long as you have it the same all the way throughout. So for example, you could use this with base 3, base 4, doesn't matter. It will also work for base e. So these three properties can also be listed exactly the same way if you are talking about the natural log rather than the common log. So let's see if we can practice some problems using these properties. So here's a sample problem that you could be asked to solve. So you're supposed to use properties of logarithms to expand this particular expression. Well, if you notice, the most tempting one to start with is the quotient rule for logarithms. So at the beginning here, we've got log of e squared over 5. Well, this is equivalent to, if you apply the quotient rule, log of e squared minus log of 5, because recall that division on the inside of the log becomes subtraction on the outside of the log. Now, the first expression can be simplified further by bringing down the 2. So this can be okay, so again, we've written this as 2 times log of e minus log at 5. And so at that point, we've simplified the expression as much as possible. So let's move on to another example. Now for this one, notice that again they said expand. So the idea is that we're going to take this small statement and go and write it as largely as possible. So we've got log of x cubed times y over z squared. Now the first thing we can do is apply the quotient rule. Here we've got log of x cubed times y. And remember that with division, it's minus, it's not plus. Minus with division. And then we've got log of z squared. Well, remember that there's that product rule, and that can be applied to the first expression. So this becomes log of x cubed. And you can write the parentheses if you want to be careful about that. Now remember, the product rule has plus, so this becomes plus log of, and that was just a plain old y, right? And then from above, this is not the product rule, this is just copying from above, we still had log of z squared. One last thing that can be done to this entire expression is that the exponents can be pulled down and changed to multiplication. So they're no longer a power, they're now times. So this is 3 times log of x. I can stop writing the parentheses if I want to here, but there's no problem leaving them in. Log plus log. And at this point, the expression is completely simplified. And remember that you don't really need the parentheses as long as you only have one thing that the log is being taken of. Okay, so next example. What we're asked to do here is actually condense the expression. So this is a different type of problem. They want us to actually condense, take this large logarithm and make it smaller. Now notice how we're using natural logarithm here. And remember, natural logarithm is just log base e. And remember, I mentioned at the beginning of the presentation that these log statements will hold for any base. So the product rule, quotient rule, and power rule will still apply to natural log in this situation. Now we've got 1/3 natural log of x plus natural log of y. Well, obviously the power can become an exponent, right? So this is natural log of x to the 1/3 plus natural log of y. Now the very last thing that you can do is obviously apply the product rule. So we got a plus on the outside of the logs, that becomes multiplication on the inside of the logs. Now at this point, if you don't use parentheses, it could potentially be debatable about whether or not y is in there. So once you've got more than one expression inside of the logarithm, parentheses are needed. So this is actually condensed. Depending on your preference, you could write x to the 1/3 as the cubed root of x. That's certainly an equivalent form. Otherwise, the expression is completely simplified. And that's it for this one. Remember to pause the video and take notes as needed. Also rewatch any parts before going on if you need to. But if you're ready, we'll go on to the next example. So this one, again, is calling for us to condense. That means apply the properties in a way that makes everything smaller. Well, notice how at the beginning here, this 1/2 needs to be distributed. So that 1/2 needs to be multiplied here and here because of the parentheses. So we've got 1/2 log of x plus 1/2 log of z minus 2 times log of y. Now what we can do at this point is we can pull the powers up. That can be our next step. So this becomes x to the power 1/2, this becomes z to the power 1/2, and this becomes a y squared. So when we rewrite all of that, we've got log of x to the 1/2 plus log of z to the 1/2 minus log of y squared. Now the plus is going to become the product rule because plus on the outside becomes multiplication on the inside. The minus is going to become the division rule because minus on the outside of logs becomes division on the inside. So finally we can write this expression log of x to the 1/2 times z to the 1/2 over y squared. And notice again, since there's several things here, we really should be putting parentheses around our final expression. The very last thing is x to the 1/2 and z to the 1/2. This is more personal preference, but one could write that as a square root of x and a square root of z if desired. Otherwise, this is completely condensed. Now remember, one of the main points involved with logarithms is that they can be used to solve exponential equations. Remember, an equation is exponential if x, or the unknown, whether it be t or y or anything, if it's in the exponent, then that makes it an exponential equation. Now, what's the answer here? Well, obviously x is 2, right? Because 4 squared is 16. But nonetheless, let's see if we can solve this problem using what we know about exponents, just as a practice. So even though we already know the answer here, 4 to the x equals 16. Well, what you can do is take the log on both sides of the equation. Now, why would you do that? Well, that's because you can actually pull the exponent down, and it's now its multiplication. Oops. Not there, of course. Down below. So again, once you've taken the logarithm, you can pull the power down. So this becomes x log of 4 equals log of 16. Last step to get x by itself, it's just x times a number. Whenever that happens, you always just divide by that number, right? Because if you had, say, 3x equals 12, you would just divide both sides of the equation by 3 to solve for x. So here, all we just have is x times log of 4. So to get rid of that log of 4, we divide by it on both sides. Now, at this point, we're almost done. So x equals log of 16 divided by log of 4. Now, at this point, notice how this expression has no unknowns in it. There's no unknown variables. So at this point, you could just go to your calculator if you need to make an approximation of the exact value. But in this case, the problem will actually turn out to be an exact value. So in your calculator, if you do log of 16 divided by log of 4, and you should check this on your own calculator, you should get 2 as the answer. Again, notice how we knew the answer was 2, but if we hadn't noticed that, we could have used properties of logs to solve this problem. So what happens when we look at a problem like this? It almost looks exactly the same. The only difference here is instead of a 16, we've got a 15. So it's not automatically obvious what x should be. Obviously, x is somewhere between 1 and 2, right? Because 4 to the power 1 would just be 4, and 4 squared is 16. This should be something between 1 and 2. But we don't really know the exact value without appealing to logarithms. So let's go ahead and do that. So we've got 4 to the power x equals 15. The technique is whenever you have x in the exponent, take log to pull the exponent down. And since you can't just take logs wherever you want to, you have to take log on both sides of the equation. That's what makes it a valid algebraic move. At that point, the x can come down, and just like the last example, we have x times log of 4 equals something. Well, we've got x times log of 4 equals log of 15. Last step, divide by log of 4 on both sides. So finally, that's going to make the log 4's cancel, and we should be able to get an exact value or an approximation of x if it doesn't come out to be an exact value. So in your calculator, do log of 15 divided by log 4. And it does not come out exactly. You get 1.9534 if you round off to 4 decimal places. So it might make more sense rather than equals to go ahead and write that this is an approximate, not an exact value. Otherwise, we're done with this one. And notice again how we got the answer. Even though it wasn't automatically apparent in the original expression. So it's just something a little less than 2 that makes this true, which makes sense. And the expressions can be complicated. So here's an example of one that's not quite as easy to work with, but we should still be fine though. So we've got 2 to the power of 2x minus 1 equals the number 32. Okay, so at this point we're going to consider what to do. Take the log on both sides of the equation. At that point, you can pull the power down, but just be careful because there's this power is actually a complex expression, 2x minus 1. So you got to make sure that you pull that whole thing down and put parentheses around it to make sure that you know that the whole thing is being multiplied by log of 2. So 2x minus 1 is being multiplied by log of 2. And this is equal to log of 32. And at this point, this is just a simple algebraic expression. Even though there's logs in there, because there's no x in this expression, it's just some number. So at this point, you can either distribute the log of 2, or you can divide by it on both sides of the equation to get rid of it. Either one will work. I think it might be slightly less work to just go ahead and divide by it on both sides. But of course, at that point, it would be up to you. You'll get the same answer either way. So if you divide by log of 2 on both sides, then of course that makes it cancel there. You've got 2x minus 1 equals log of 32 over log of 2. So if you do log of 32 divided by log of 2 in your calculator, what happens is that you get an exact value, and the exact value is 5. If it had been a decimal, it might be a good idea to save the rounding until the last step. That way you'll always get the most accurate from a rounding perspective. But since it does turn out to be fairly even, then if you do 2x minus 1 equals log of 32 over log of 2, which is actually 5, then to finish solving for x, you can add 1 to both sides. 2x equals 6, and the very last step, divide both sides by 2, and the final answer is that x equals 3. Now, remember, in math, a lot of times you can check your answer if you have an opportunity to. Here, you do actually have an opportunity to check your answer because you had an original expression and you're trying to solve it for x. So whatever you get for x should satisfy the original. Well, if you imagine x equals 3 being in here, you get 2 times 3 is 6, right? Minus 1 is 5. And 2 to the 5 is indeed equal to 32. So we did solve this exponential equation. Notice how you could have guessed if you worked with the original and guessed that x was 5, but if it had been a decimal value for x, you would not have been able to just guess it. You would have needed to go through the process of logarithms to solve it. Let's take a look at this example. We've got e to the x plus 1 equals 1 over e. Now, that would be perfectly fine to take the log on both sides of this equation. That would definitely get us to the answer. But whenever you see e, it usually turns out to be slightly less work to take the natural log as opposed to the common log log. Although I do want to emphasize, if you took log on both sides, that would work out fine as well. So we're going to take natural log on both sides of this equation. And what the log properties allow us to do, since they also hold for natural log, is it allows us to pull the power down. Remember, that whole power is coming, not just the x. The whole exponent has to come down. And we need parentheses here because of the fact that it's going to be the whole thing multiplied by what's left. And what's left is natural log, and then the base is e here, and then still equal to natural log of 1 over e as above. Okay, so what's next? Well, you can jump to your calculator and start evaluating things like natural log of e and natural log of 1 over e. That would be completely fine. Another path you can take is you can solve some of this without using a calculator. Remember that natural log of e is the same thing as log base e. And if that were equal to some quantity, what that means is that e to the power x equals e in this situation. So the only way that e to some power is going to be equal to itself is if x equals 1. So natural log of e is just the number 1, and since you're multiplying by x plus 1, that just becomes x plus 1 times 1, which is just x plus 1. So natural log of e is always just equal to 1. If you want to remember that and not go through the proof each time, you can. And then still go in here, so natural log of 1 over e. Well, natural log of 1 over e, notice how 1 over e is the same thing as e to the negative 1. And then if you pull the power down via the power law, this is negative 1 times natural log of e. Well, remember that natural log of e is just 1 itself, so this quantity over here is really just negative 1. Finally, we can solve this equation. We need to get x by itself. We need to get rid of the positive 1, so we subtract 1 on both sides of the equation. Well, what are we left with? X equals negative 2. And that's our answer. We can even check it in the original expression, because if you had negative 2 in there for x, you'd get e to the negative 1 total, which is the same thing as 1 over e. So it works out. And that gave us our answer. And that concludes this lesson. Thank you for your attention. Be sure to take notes as listening and review and rewatch the video as needed.